Name is Ashley, and my presentation today is going to be on a group of chemicals called per and polyfluoral alkyl substances. For the remainder of my presentation, I'm just going to call it PFAS because it's way easier than that mouthful. So what these chemicals are is, again, they're a group of chemicals, and they're an emerging environmental contaminant. And when I say emerging, I mean emerging because we're really just starting to scratch the surface on what we know about them in terms of how they interact with the environment, the health implications, or even identifying all the different types of PFAS compounds. I'll discuss it a little more as we go on. But it is important to start off with a little bit of background information because it involves a little bit of a scandal. So PFAS was invented in 1930s, 1940s, so think your Cold War era. At the time, there was this push for better living through chemistry. And now what that means is there is this belief that a lot of our problems could be solved by coming up with different chemical solutions. Like all these different chemicals could really benefit humanity. And because this was a newer science, there wasn't any sort of any government oversight or regulation. They were all on board. And again, this is our Cold War era, so we're also looking to these chemical manufacturers for war supplies. So think of your Agent Orange, your DDT. So the government was very pro chemical manufacturers because they were helping them in this war. So it wasn't until about 1976 that the government was kind of on board and like, hey, this isn't a good idea, and they introduced the Toxic Substance Control Act. However, this didn't actually impact PFAS because it was allowed to be grandfathered in. So they realized that they let this regulation go, or unregulation, I should say, go for so long, and there were so many chemicals that they now needed to regulate that if it was invented before the Toxic Substance Control Act, it was grandfathered in. So the chemical companies, if they noticed there was any sort of environmental health or environmental harm or human harm, they were expected to self-report it. Whereas this is where the situation gets a little sticky. So bring in DuPont, a chemical manufacturer. In the 1990s, there was this farmer who realized his cattle started dying, and he wasn't quite sure why, but he was fairly confident it had to do with, again, the chemical manufacturer DuPont. And it took a couple of years, but he was finally able to get in touch with a lawyer who would fight for his side. Through this litigation is what we discovered on PFAS and why we're starting to study it. So through internal court documents, it was found that DuPont kind of knew there was something up with PFAS, that it wasn't good for the environment and it wasn't good for human health. And so again, this was around the mid 1980s. PFAS had been invented 1930s, 1940s, and this case took place in the 1990s. So DuPont had at least a decade of knowledge from between when they recognized there was this environmental and human health hazard to when this lawsuit was brought about, where they continued to deny that there was any sort of harmful impact that this chemical had. But this created one of the largest medical studies that was done in pretty much human history on what this substance could do to the body. But it focused on two particular PFAS compounds, PFOS and PFOA, which is where most of our knowledge of these compounds comes from. However, like I said, this is a group of chemicals. So PFOS and PFOA are just two of thousands. So again, we're just starting to scratch the surface, and due to the chemical structures, each of these compounds operates a little bit differently, which I'll get into a little bit later on. If you are interested in hearing more specifics on this case, I did add a supplemental document to Blackboard. It is 50 pages, but for the court case, You really just need to read the abstract and the introduction. And the appendix has some of those internal documents from DuPont, including board minute meetings where they start discussing these hazards. And the paper as a whole kind of goes into some of the reasons why DuPont may have chose to hide this information if that's something you're interested in. But again, it's an optional document. You can download it to read it later. I know you guys have a lot going on with finals right now, and it is a little bit longer. So let's jump into it. What is PFAS? Again, that means per and polyfluoroalkyl substances, and these are anthropogenic, so they are man-made chemicals. And you'll hear me talk about this on almost every slide today, but it has a strong carbon-fluorine bond, and this is what gives PFAS its unique properties. Carbon and fluorine don't typically bind in nature, so this is a man-made bond or man-made chemical bond, and it's extremely stable. Once it's together, it's really hard to break it apart. And again, as mentioned on the previous slide, PFOA and PFOS of these thousands of chemicals are the most common. So for this next part of my presentation, don't get freaked out by the chemistry. I'm going to try to break it down as easy as possible. What I want you to be able to do is identify a PFAS compound based on its chemical structure alone. So we're going to start out, if we refer back to my first bullet point, I have the name broken down into 3 different color categories. So we're going to be working through the name backwards. So the first term we have in dark blue is alkyl. So what an alkyl group is, it is a carbon chain that is bound by hydrogen. So let's look at our molecules. On the right side, I have a non-PFAS molecule. So this is not PFAS. Right above is a PFAS molecule. So again, let's find that carbon chain. So where the carbon chain is, it's in the center of this molecule. So all of our carbon atoms, although they're not labeled, they're at all of these hydrogen intersection points. So where those hydrogens meet that center line is a carbon. So how many carbons do we have in our carbon chain? Well, we can go through and we can count all these intersections, or we can look at the name and it'll tell us how many. So here we have octonic acid. So oct means 8. So go ahead and count them. We have 8 carbons in our carbon chain. So again, this is an 8 carbon chain molecule. Here we have our hydrogens that are bound by all these carbons. So this rectangle, that is our alkyl group. So now let's move to the PFAS molecule. So our carbon chain. So again, we have our carbons in this center line, and we have perfluorooctonic acid. So that prefix oct tells us, again, we also have 8. However, there is a slight difference. So I just said an alkyl group is a carbon chain that is bound by hydrogen. But in PFAS, we don't have hydrogen, we have fluorine. So let's back it up a term. So in red, I have fluoral. So this term fluoral tells us that our alkyl group will be made of fluorine. So here we can see our carbon chain, and we have our fluorine molecules. So now it comes down to how many fluorine are we going to have, which is where our term per and poly come into play. So again, we have perfluorooctonic acid, and we can see every hydrogen that was in our regular octonic acid is fluorine. So what that means is the term or the prefix per means every. So per every hydrogen, you will have fluorine. And now poly, for the purpose of this lecture, what I want you to know is poly means some or a few. The naming convention gets a little bit more difficult and a little more chemistry intensive. And again, I want this to focus more on PFAS itself. So again, per means per every hydrogen, whereas poly just means a few. So an example of that would be, so again, the top molecule has all of these fluorine, but if we had a polyfluoral alkyl substance, we could have just 2 of these hydrogen be fluorine. We could have 3. Really, any number greater than 2 and less than the carbon chain. So take a moment and pause this video. I want to give you a chance to try and identify what a PFAS compound is on your own. All right. So if you said the compound on the left, you'd be correct. So we can tell this because we have our carbon chain in the middle, but you may notice a little bit of a difference in this compound. We do have oxygen. So with PFAS, we are focused on that multiple carbon fluorine bond. So we can see that we have several of these carbon fluorine bonds, which tells us we have PFAS. So in this case, this random oxygen thrown in isn't really important for us. What we want to focus on is that carbon fluorine bond. So this is a newer PFAS compound called Gen X. And what I have on the right is a type of plastic. So again, this one is not PFAS, the one on the left is. I took this screenshot on April 14th, so just like a couple days ago, depending on when you're watching this. But as of April 14th, the EPA compiles a master list of all known PFAS compounds. There's over 9,000 of them currently. And I took this screenshot to show you too some of the differences in chemical structure. So they're widely different. And the different chemical structures really determine a lot of the properties that the chemical has. So it'll create some difficulties later on, which I'll discuss. I also do have this picture hyperlinked if you download the slides, if you want to go through and scroll through a couple. So going back to that carbon fluorine bond, what that gives us is this hydrophobic tail. So hydrophobic, water repellent. However, on that flip side, we have a hydrophilic functional group. So hydrophilic, water loving. It really wants to dissolve into the water. So just in this one compound, we have these 2 juxtaposing reactions to water, which will lead to some interesting things. So what's the purpose of this? Why did they even think to make it? Well, one benefit, it's a water and grease repellent. So some examples of use for this benefit include nonstick cookware. So think Teflon. Another use is stain and water resilient fabrics, as well as packaging. So when I say packaging, think like fast food packaging. So you go to McDonald's and like you get a cheeseburger and it comes in that like oddly paper, but not really paper wrapper. So the purpose of PFAS and something like that would be so the grease doesn't completely soak through the paper and like mess it up while you're holding on to it. So the good thing about PFAS, it's grease repellent in that sense. Then it's also used as a surfactant, and surfactants can be used in a variety of fields. This is just a small overview, but it's used as a surfactant in electronics, cosmetics, the medical field, cleaning products, and again, the list just kind of goes on. It is also resilient to degradation, even at high temperatures. So the most popular use for PFAS is firefighting foams, followed by flame retardants, which is like carpets, safety apparel. You could even put nonstick cookware into this category. And now some of the disadvantages. So it's water and grease repellent, and it's resilient to degradation. So if we go back up to the benefits, it's a catch-22. Its benefits are the same exact things that create its disadvantages. So first, it's, again, water grease repellent. So this repellency, or it creates an impermeable external layer. So that makes it hard for chemicals to get in there and to break up the bond. It also makes it hard for microbes to degrade it. And again, it's resilient to degradation. So it's resilient to thermal degradation because it's so strong at high temperatures. It's resilient to chemical degradation because of how strong that bond is. And for the same reason, it's resilient to that biological degradation. And this can lead to bioaccumulation in the food chain. So I know we're all from different backgrounds. So if you're not familiar with the term bioaccumulation, what this is it means that the contaminant goes up the food chain. So say we have this worm and it's crawling through some PFAS contaminated soils. So later this worm is ate by this turkey. The worm wasn't able to process the PFAS, so it just stayed in its body. And now all the PFAS that worm has consumed has gone inside of this turkey, and that same process occurs. So the turkey can't break it down. So PFAS has the ability to stick to proteins. So PFAS will stick to the proteins in the turkey's blood. And now it's Thanksgiving and we're eating turkey. All that PFAS the turkey had is now going into us. And the same thing could be said for the pictures that I have on the left. It's just a different it's just a different environment. So this is more of an aquatic type of setting. So you have fish swimming in contaminated waters that eventually get ate by a bear, but it's the same principle. It travels up the food chain. It is also soluble in groundwater, which I will talk about a little bit later on, but it is important to note that it is very soluble. So how do we get it in the environment? Well, one of the ways is from wastewater discharge through PFAS producing plants. And where we're at, the most common way you can get it into the environment is through firefighting foam at military and firefighting training facilities. There is also PFAS that can be there's also PFAS contaminated soils that are transported by water and wind, and this is part of a natural earth process. So you always have soils that are being transported by water and wind, just again as a natural earth process. So when you have those soils that are contaminated, they're still able to flow with that natural pattern. So that's how you can get kind of some of that contamination. And then there is also the application of biosolids to land. So kind of going back to that idea of transport, water, sediment, and biota are the most important compartments for PFAS storage in the environment. And that hydrophilic group really opens it up to the possibility of long-range transport in aquatic ecosystems. So think your marine environments, your freshwater environments, even through the groundwater. Then kind of a newer area of research, or has a little bit of focus on it right now, is the sorption. So soils that have a higher amount of organic content have higher PFAS sorption rates. So what that means is the more organic content you have, the more likely PFAS wants to stick to it. Also going along with that, the length of the carbon chain determines how readily PFAS will adhere to the soil. So if you have a carbon chain of 8 or more, it is more likely, the PFAS compound is more likely to sorb to the soils. So let's think back to that first kind of slide that I had where we were looking at how to name PFAS on its chemical structure. That would be considered a long chain PFAS compound because it had an 8 carbon chain. So that one is more likely to sorb to the soils. Whereas if you have a short carbon chain, which is less than 8, it is more likely to transport in water. Now, this is an important concept to keep in mind because let's go back to our first unit for this course where we were talking about aquifers. So we have our vadose zone, which is our unsaturated zone. So if you know what sort of PFAS contamination to expect in an area, you are able to better narrow down where to look for it. So say you have a PFAS compound with a 12 carbon chain, it's likely to hang out in the vadose zone a little bit longer than a shorter carbon chain with, say, 3 would. But again, that hydrophilic functional group, it still does want to dissolve in water, so eventually it will reach the groundwater, infiltrate into the groundwater. So human exposure. So it's been shown that more than 95% of the US population has been exposed to PFAS and has measurable concentrations in their blood. So it's very likely that most of us in this class have some sort of PFAS concentrations in us currently. So this can occur through a couple of different ways. The biggest one is ingestion. So think back to that turkey example. We can get it through contaminated foods. We can also get it through foods that were grown in contaminated soils. You can also get it from foods that have been cooked on PFAS containing appliances. So Teflon, your nonstick cookware. I would honestly recommend, if you guys are using a Teflon pan, that you switch to cast iron or stainless steel. You can also be exposed to PFAS through occupational exposure. So a lot of our first line responders are firefighters, military personnel. If they're using a lot of those firefighter extinguishing foams, they're likely being exposed to PFAS. You can also be exposed through direct contact with consumer products. So going back to that fast food packaging, so by direct contact with that, you are being exposed to PFAS. And many personal care products contain this chemical. So some of our lotions, our shampoos, our hand soaps, nail polish, they all have PFAS in them, or many of them, I should say, have PFAS in them. You can also be exposed through the inhalation of ambient air and dust. This one isn't as common for us, because we're not as large of a manufacturing country anymore. However, in the countries that are large PFAS producers, so like China and India, this is more of a problem. You can also be exposed through contact with contaminated soils. And now, why should we care about this? So what if we have PFAS in our blood? So a lot of the health impacts, going back to that DuPont case, we know the most on PFOA and PFOS. However, there are, again, thousands of chemicals that we still really need to study up on. There is actually no MCL for PFOA and PFOS. However, they have issued a health advisory. And this health advisory is 70 parts per trillion. So thinking back to some of the other things that we've learned in this course, when we were talking about maximum contaminant limits, all of the parameters we were looking at were listed in parts per million and parts per billion. So parts per million is pretty small, parts per billion, very small. Parts per trillion is a logarithmic scale, smaller. So these are very, very tiny concentrations that are going to have really big health impacts. Some of these health impacts are high cholesterol, testicular and kidney cancer, ulcerative colitis, thyroid disease, pregnancy-induced hypertension, as well as reproductive and development impacts. So on the left is a picture of a baby. So when DuPont became aware that there may be some human health impacts on, there may be some human health impacts on its employees due to the PFAS exposure, they pulled all of the women of childbearing age off their Teflon production line. Now, they didn't tell the employees why they were doing it. It was kind of a no questions asked type of situation. Um, However, we can see that this baby was born by one of the women who was on that line, who was pulled off. Um, he was born with nasal and eye deformities due to his mother's exposure during her pregnancy. So it does have some pretty big impacts. And again, this is at tiny concentrations. So knowing how to collect samples for this is going to be a key thing coming up in the next couple of years, because we're really just starting to scratch the surface on where this is happening. So how do you collect a water sample? PFAS is a little bit more stringent than some of the other parameters, such as like pH or electric conductivity, because there's a lot of ways you can get contamination into your sample. So the first step is probably one of the hardest, and that's making sure your sampling equipment, as well as any personnel involved, are free of PFAS. So some equipment that may contain PFAS. If you do a lot of field work, you may know what a Write in the Rain notebook is. It's a water resistant notebook, so it allows you to take notes like the name suggests, it allows you to take notes like in the rain or for water sampling. When I go out and collect my samples, I like taking it in case I spill on my notebook. However, for collecting PFAS, this would be considered a source of contamination. Sharpies would also be considered a source of contamination. And you wouldn't be allowed to wear any water resistant clothing. You would have to be wearing natural fibers such as cotton. And then the day of sampling, you also have to be very cognizant of what you do while getting ready. So you can't wear any lotion before you sample, and you have to be aware of what's in the shampoo that you're using in case it may have PFAS, and you also are not allowed to have your nails painted. And these are just a couple of examples of contamination. There are tons of different things that could have PFAS in them. So once you've made sure the sampling equipment as well as yourself are free of PFAS, you then have to wash your hands. However, a lot of soaps may have PFAS in them, so you have to use special solutions in order to make sure your sample isn't contaminated. So then, after you've made sure you're free of PFAS, your hands are clean, you also have to put on a pair of gloves. And once these gloves are on, you can't touch any surfaces. If you do touch something, you have to start the process over where you wash your hands and put on new gloves, because it will be considered a source of contamination. So when you get a PFAS sample, typically you'll call a lab in advance to let them know you want a sample for something, and they'll give you the supplies you need while you'll take it back and they'll analyze it. So on the sampling day, you'll collect the sample by filling the bottle the lab has provided, and this bottle will contain a preservative in it. And when you're collecting the sample, the cap can't touch any other surface and it can't be placed on the ground. So you have to pretty much hold it in your hand while you're filling the bottle. So you have your bottle filled, you've capped the sample. In water, there's the rule of threes. So you'll mix that bottle 3 times and dissolve the preservative. And once it's closed, you can't open it, because any sort of PFAS that may be lingering in the air, if you were to open it, it's now no longer considered a representative sample, and you'll have to recollect that sample again. The lab will take it after it's been capped. So after you get your sample, you'll then collect a field blank by pouring pure water into one of the bottles. So what this field blank tells us is any sort of background levels of PFAS. So in your initial sample, say you have 20 parts per trillion of PFOS. If your field blank shows 5 parts per trillion of PFOS, you can take the 20 minus the 5, and therefore your water sample has 15 parts per trillion. So it's a little bit more of an accurate way to understand what's in the water and what may be that background noise or floating around in the air. And with all water sampling, you really want to make sure you get some site characteristics in there. It's a little more important for PFAS that you get the types of pipes and fittings because these materials could be maybe a source. But you also want to make sure you get the time, some different sort of site characteristics, as well as the weather conditions. You will also fill out a chain of custody form since it will be sent off to a lab. So what a chain of custody form is, it's a list of everyone who handles your sample. So in the field, if I were to collect the sample, my name would go first. Then say I have someone deliver the sample for me. So say Dr. Lencheski takes it to the lab. Her name would go after mine, as well as what she's done with the sample. And then upon receipt, the lab will also fill out the chain of custody form, and whoever analyzes the sample will fill out as well. So that way, if something goes wrong or if there is a source of contamination, you can go back up the list and figure out where it occurred. And you're going to repeat this for every sample you take, and every sample will require your hands washed again, as well as a new pair of gloves. And again, that's to prevent contamination. So the detection methods, there's still a bunch that are being come out, or there's still a bunch that they're trying to come out with. And because again, this is a newer area of research. So for drinking water, the EPA has method 537.1. And I realize I have a wall of text on the left side. This is just more of a detailed description. What I really want you to know is on the right side of the screen. So what EPA method 37.1 is, it's detection by solid phase extraction and liquid chromatography in tandem with mass spec. And this will measure 18 different types of PFAS in drinking water. So those 18 types of PFAS are the bottom half of your left screen. And again, I'm not expecting you to memorize these. This is just kind of a little overview into what they are. At the bottom, you can see an example of the polyfluoroalkyl substances. And this name might tell you a little bit why the naming convention is a little too much for this lecture, because it does get pretty complicated. And then I also, up at the top of the screen, I have a summary of the method through the EPA that goes a little more in depth if chemistry is your thing and you want to learn a little bit more about it. I will talk about solid phase extraction, just kind of going into an overview of what it is. We did talk about liquid chromatography and mass spec earlier in the course, so I'm expecting you to already have that knowledge. But what solid phase extraction is, it's when compounds are dissolved or suspended in a liquid mixture, and then they're separated from the other compounds by physical and chemical properties. So for PFAS solid phase extraction, what it does is there are these cartridges that the water is passed through, and the cartridges contain polystyrene divinyl benzene, or SDVB, and that is the sorbent material that PFAS is going to stick to. This then, once it's passed through that cartridge, it can be separated out through a tiny bit of, or with a tiny bit of methanol. So here's just a list of some upcoming methods from the EPA. So this includes the ambient air, as well as just total types of PFAS in different environmental samples. Many of these are expected to be finalized by the end of 2021. So hopefully we'll have a couple more methods to find different environmental sources or different compartments of PFAS. So where do we have it? I've now gone through what it is, why it's bad for us, and kind of some of the issues with that carbon-fluorine bond. So now we're going to go into actually where it's at. So here I have a map, and I want you to first take a look at what these color codes mean. So the purple is for our military sites that have been found to have PFAS contamination. Our blue teal is from drinking water sources, and the orange is just other known sources. So take a look at Illinois. You can see we only have a handful of dots. Now let's go a little bit eastern, and we can see Michigan is kind of a hot spot, and we can see the East Coast as well as definitely North Carolina has all these PFAS sites. So what does this mean? Does this mean that we have less PFAS in Illinois? Unfortunately, it does not. What this map is showing us is that we don't test as much for PFAS as some of our neighboring states, such as Michigan, do. So, Michigan, after the Flint water crisis, they really vamped up their water quality testing. So, they were a little more concerned on what was going on in their water. So, Illinois we're working on it, but we're not quite there yet. Which leads me to my next map. This is from the Illinois EPA, and I have it zoomed in on DeKalb in particular. So when we look at this map, we can see all these orange dots, and it appears that we have all these sampling points. But if we look at what that orange color actually means, this is the total that needs to be sampled still. So we can recognize that we do have to look for this compound, but it's just a matter of timing and resources. However, coming up, Dr. Lincheski and Dr. Brown actually have a grant to study PFAS in DeKalb. So NIU is going to be the first in DeKalb to actually quantify this locally, which is really exciting. So we're also going to take a look, go a little bit northwest into this town Freeport. So we can see Freeport has all these blue dots and one red dot in the center. So what this is the below minimum report. So the blue dots are below minimum reporting level. So it's been shown that PFAS is present, but it's less than 2 parts per trillion. But still there, and it's still, again, because that health advisory is such a tiny number, even when you have these small amounts, definitely worth noting. And then we can also see we have just one hot spot. So we're going to use Freeport as a little bit of a case study. So zooming in on the city, we can see that there's a couple of Army stations nearby. These are actually recruiting stations, but we do have one military base. And there's actually a geology graduate student whose unit is based out of Freeport. We also have this Honeywell plant. So PFAS is not manufactured in the United States. However, it is handled. And the Honeywell plant does handle PFAS. And again, we also have one of the most common sources of contamination is through those military and firefighter training bases where they use the firefighting foams. So we've got a little bit going on. Now, I took a screenshot from their water quality page. So between 2014 and 2017, when they were testing for PFOS, there was 180 parts per trillion. During that same year, or that same 3-year span, there was 59 parts per trillion. And this is the maximum amount they found. I couldn't find a range that they had detected. So again, just the maximum. But of the two, we bring that to a total of 239 parts per trillion. So our health advisory, 70 parts per trillion. This is nearly 4 times the amount that's recommended by the EPA. And this means that a lot of people in Freeport are being exposed to this threat. So what's being done about it? We can tell it's an environmental hazard. We know that there are these human health impacts. We don't really know where it's at yet. Well, in 2006, PFOS and PFOA were voluntarily phased out in the United States. So these big chemical manufacturing companies, DuPont and 3M are the two big ones. They got together and they agreed, you know what, we'll stop this. What problem we're facing now, because again, if we look at Freeport, even though they phased it out in 2006, we still have contamination, high amounts of contamination from 2014 to 2017. So what these contamination levels we are seeing are legacy sites. And we're also still getting PFAS, or we're still using PFAS. We're just not producing it. So some of these legacy sites have been around. Again, PFAS was made 1930s, 1940s. So we're talking about 80, 90 years. There are a couple removal techniques, though, that we're working on. So some of these include, and I have them going in order from the best to the not as well. We have photocatalyst, reverse osmosis, and then followed by membrane filtration. So what photocatalyst remediation is, it's used as a pump and treat. So you pump out the contaminated water to treat it and then put it back. So the water is passed through UV light, and in combination with an introduced catalyst, this creates a chemical reaction with PFAS that will help break it down into different components. So the pros, it has shown 100% degradation of PFOS in 60 minutes. Another pro is that there's a low risk of secondary pollution. So when PFAS breaks down, it has the potential to break down into other PFAS components or other hazardous substances. So with photocatalyst, you're not going to see this sort of bad breakdown. And it's pretty cost effective. So the cons of this, it needs a lot of energy. So it's got a high energy use, which makes it hard to use for large quantities. And these photocatalysts can't be reused. Which brings me to reverse osmosis. So what reverse osmosis is, it's when contaminated water is run through a semi-permeable membrane, and this separates ions and large molecules from the water. So the benefits, it removes PFOS at levels of 0.5 to 1600 parts per million. So the cons. So think back to our maximum contaminant limit. So that is, again, 70 parts per trillion. So 0.5 parts per million is higher than that health advisory. So if we were to use reverse osmosis, it's not going to bring down the contamination to a small enough level where it's negligible to human health. What this is good for, though, is if you have a very contaminated site, it does help bring down that contamination to maybe a more manageable level. But again, it's still going to be considered hazardous for us. And it's also a pretty energy intensive process, and it's not really cost effective due to the high energy cost that's going to cost. And the last removal technique is membrane filtration. So this is when contaminated water gets run through a nanopore filter. And the pros, it's shown a 99.5% removal rate. And it's also better for linear isomers of PFAS. So PFAS has both linear and branched isomers. So the linear isomers, they are more persistent in the environment. So think like your soils, your overall geology, as well as organisms. So your plants, your animals. So it's great for environmental health. Now the cons of this is there is a high amount of secondary pollution because this is not a chemical reaction. It has nothing to do with the chemicals at all. So what this does is it displaces the pollution. So rather than the pollution staying within the water, it stays within this filter. And now you have the issue of what do you do with this PFAS contaminated filter to prevent more contamination from occurring? These nanopore filters also have nanopore membranes also have a pretty high cost associated with them. And it's also been shown that the higher the pressure, the higher the performance. However, that's going to increase your energy inputs, so it'll increase your cost as well. And now going back to the isomers, so it's still being researched on why, but humans tend to hang on to the branched isomers. We're the only organism this is seen in. So although other plants and animals hang on to the linear ones, if we use this membrane filtration, yes, it's great for environmental health, but from a human health perspective, it's not going to be our first option that we choose. So what are some things that we should take into consideration when we're talking about removal? Well, the first thing is that many of these removal techniques, they've been done on freshly introduced PFAS contaminated soils and water. So in a lab setting, scientists introduce PFAS and they maybe let it sit in the water for minutes, days, weeks, and then they remove it. Well, since this is freshly introduced, it isn't trapped or fully absorbed to the soils yet. So there's this concept called desorption hysteresis. So when a chemical sits in some sort of porous media, so think soils, for a long period of time, it creates this complex matrix where that matrix makes it harder for the chemical to be removed. So when you have these legacy sites, which we have some that have been out for decades, they're going to have lower efficiencies seen than on the lab studies, because again, those lab studies, it's a new contamination source. So it doesn't have as complex of a structure yet as somewhere that's been contaminated for say 40, 50 years would have. So although we can go back and say this membrane filtration and the photocatalysts have 99.5 and 100% removal rates, in the field setting, that may not be the same efficiency. It will most likely be significantly smaller. Another thing to keep in mind is that PFAS compounds are complex and they have different reactions to different removal technologies. So let's go back to one of my slides. So these have very different structures. So these different structures are going to determine how they react to the removal technologies. No two are going to act the same. So again, we're having to prioritize and come up with different remediations for different PFAS compounds, as well as almost like a trial and error to see what works best for one compound may not work the best for another compound. And then another thing to keep in mind is going back to our carbon chains. So again, a long chain carbon is 8 or more. These long chain carbons can break down into shorter carbon chains. So this poses an issue because if we're not being cognizant of it, the shorter chain compounds, they are more toxic and more persistent in the environment. So while you may be removing a large amount of large chain PFAS, if it's just breaking down into shorter chains, you're creating an even bigger environmental health hazard than if you would have left the long chain PFAS. So again, this is a very complex chemical and it's really tricky to figure out how to manage and how to navigate. And I did mention that I had a supplemental document on Blackboard. However, again, finals is coming up. I know you guys are busy. If you would like maybe a little more fun way to learn about it, there's a movie called Dark Waters. It has Anne Hathaway and Mark Ruffalo in it. It's on Hulu Showtime. You can get like a free student 7-day trial. I'm not sure. I'm sure it's on other platforms. I don't know of any others off the top of my head. But it's a movie that was based on this story. It goes over the DuPont litigation. It definitely focuses more on the law side, but it does discuss the chemical and everything in the movie, even though it's not a full-on documentary. It's like I said, it's a movie based on a true story. It's still fairly accurate in what happened with the case and the science behind it. I also, if you want to do like a little preview, I have the trailer hyperlinked. And that is all I have for you guys. So I hope you enjoyed PFAS. That is all I have.